Hi class, this is chapter 6.3, Exponential Functions, part 1. Okay, so let's say we have two business owners. They're both going to start with 75 stores, and they have two different business plans. So business owner A wants to increase her stores by 20 each year. So she'll go from 75 stores to 95 stores to 115 stores, etc. Okay, adding 20 stores each year. Business owner B also starts with 75 stores, but she wants to increase by 20% each year. Okay, so let's see how many stores business owner B will have at the end of each year, and then we'll see who seems to be doing better. Okay, so business owner B is starting with 75 stores, and then she's going to add 20%. So we have to figure out how many stores is she adding. So 0.2 times 75 would give us 15. So she's starting with 75 stores and adding 15 stores. So she would be at 90. Okay, so just under her competition. Her competition has 95 stores at this point. Okay, what about year 2? Okay, so she's still going to start with 90 stores, and then she's going to add 20%. Okay, so she's starting with 90, and then she'll add 18 stores. This will bring her to 108. Okay, so still lower than her competition, who is at 115 stores. Okay, year 3, so at this time we have to start at 108, add 20% of that. So we're adding 21.6 stores, which would be 129.6. If you don't like that 0.6, since we're talking about number of stores, you could just go down to 129, or think of it as she built most of the store one year and then finished up, in January of the following year. That's fine too. Okay, we could keep going this way, but it kind of gets tedious. Like if I want to know how many stores she's going to have on the 8th year, I would have to calculate all these ones in between. Okay, so there's actually a faster way of doing it if we just want to jump ahead to year 8, or especially if it was way down the line at year 20 or 50 or however long we think she's going to be in business. Okay, or her company's going to be in business. Okay, so let's try to find a better way of writing all this. So going back to the beginning, I have 75 plus 0.20 times 75. Well, this is equivalent to 1.20 times 75. Okay, so think of this 1.20 as representing, so 100% of the 75 stores, right? And then she's going to add 20% of those 75 stores. So 1 plus 20% is 125%. So that's how many stores she has in that second year, since she has all the ones that she started with plus an additional 20%. Okay, same thing down here with the 90 stores. So that's 120 times 90. Okay, but if you notice, 90 is what we got when we added 75 and 15, meaning it was this 120 times 75. So I could write this guy, this 108, this is really 1.2, and instead of times 90, that was 1.2 times 75. Okay, down here I have 108 plus 20% of 108, so that's 1.2 times 108, but the 108 I got from the line above, which was 120, or sorry, I should say 1.2, right? 1.2 or 1.20 times 1.20 times 75, right? So I was just writing down this line right here since it's equal to 108. Okay, and then hopefully you see that this can be written a bit neater, right? This is equivalent to, So 1.2 and 1.2 and 1.20 are the same thing, right? So 1.2 times 1.2 times 1.2, well, that's 1.2 cubed times 75. Okay, back here, this is 1.2 squared times 75, 1.2 to the first power times 75. Okay, so the next one, we would start with 129.6 and add 20% of that. Well, this is the same thing as 1.20 times 129.6, but that's the same thing as 1.20 cubed times 75. So we really want 1.2 to the fourth power times 75. Plug that in, and this is equal to 155.52. I'm just going to use 155.5 in the table, okay? But again, if you want to use 0.52, that's fine. Okay, and also even if you want to round it to the nearest store or round down, either one of those makes sense. Okay, so the fifth year, this would be 1.2 to the fifth power times 75. So 186, and I'm going to round this to 0.6. Okay, so let's see if she's doing better now, or if this business owner is doing better. So at year 4, notice at year 4, they're pretty close. 155 stores versus 155.5 stores, right? So basically the same at year 4. But then year 5, business owner B pulls ahead. Okay, let's just skip down to 8. So this would be 1.2 to the 8th power times 75. So this is 322.5 stores, whereas her counterpart only has 235 stores. So she's ahead by 87 stores. So she's doing much better by year 8. Okay, let's look at these two on a graph. So there's table B completed. Okay, business owner A. So she was the one that just wanted to add 20 stores each year. Okay, so if we just keep adding 20, looking at rise over run, or y2 minus y1 over x sub 2 minus x sub 1, you will get that m is equal to 20. The y-intercept is 75. That's how many stores we're starting with. And we get this nice linear function. Okay, what about business owner B? So she's starting at the same place, 0.75. Then she's at 90, so just slightly less than her competition, who's at 95. Then 108, so again, less. 129.6. Getting closer. Year 4 is where we said they were pretty even. I must have missed a number. That's okay. Or I think 129, so that's here, right? Okay, good. And then year 5, 186. So that's where she really pulls ahead. Business owner B really pulls ahead. Okay, and then 6 is 223, 267, or 268, I mean. So this only goes up to 250, so she's way ahead, kind of off the table, okay? So we see that this is, that's kind of a little too wobbly, but it increases very dramatically. Okay, so here it is on Desmos. And then I adjusted the scale, so we're going all the way up to 350 now. Okay, so again, you have linear growth, so in black, versus increasing by 20% each year, which is an example of exponential growth. Okay, so sometimes it's slower, it is slower in the beginning, but once you take off, you really take off if you have exponential growth. Okay, so let's look at a few more examples of exponential growth. Okay, so we're going to look at y equals 2 to the x. Okay, and so I made my t-table and I filled it in for you. Keep in mind, if you have 2 to a negative power, so 2 to the negative third power, remember bring this down as 2 cubed. So that's where the 1/8 came from. 2 to the negative second power is 1/4, etc. Okay, so when we graph these, and I'll start here at 0, 1, so I'll start at my y-intercept. Then we'd have 1, 2, and then 2, 4, and 3, all the way up at 8, right? So that's probably off the table even. -1 was at 1/2, -2 was at 1/4. Okay, so again, it starts off pretty slowly, but once it takes off, exponential growth really takes off. It increases very dramatically. Okay, in the last table, we were kind of starting. We were starting when time was equal to 0. Okay, and just going to the right. So we only had this portion of the curve, but in general, you'll have both sides of the y-axis. Okay, so we'll plug in both negative x values and positive x values. All right, so here's your graph on Desmos. So y equals 2 to the x power, an example of exponential growth. Don't get it confused with y equals x squared, which is our parabola. Right, so the difference is in a parabola, the base is x and the exponent is 2. That's now switched. The base is 2 and the x is up in the exponent. Okay, so they're two completely different functions. Okay, so here is 2 to the x, which we just did. Y equals 3 to the x looks very similar to 2 to the x. Okay, 3 to the 0 power is 1, just like 2 to the 0 power is equal to 1. 3 to the first power is 3, and 3 squared is 9. Okay, whereas for 2 to the x, we have the point 1, 2, and 2, 4, right? So 3 to the x is going to increase faster. Okay, but obviously the shape of the two graphs is very similar, both exponential growth. Okay, and then if we have 10 to the x power, right? So again, the graph looks similar, still goes to the point 0, 1. Okay, 10 to the 0 power is 1. But now if I plug in 1, I'm at 10. If I plugged in 2, I'd be all the way at 100. So 10 squared is 100. So exponential growth increases very dramatically. 2 to the x, 3 to the x, 10 to the x. They will all be increasing quickly. Okay, obviously 10 to the x of these three is the fastest. Okay, then we also have e to the x. So e is an irrational number, it's about 2.7. So the graph of e to the x is in between 2 to the x and 3 to the x. Again, since e is approximately 2.7. Okay, so we have the point 0, 1, right? So any number to the 0 power is going to equal 1. 1 comma e, right? So here we're at approximately 2.7. E squared, someplace here between 7 and 8. Okay, so again, it would fit right in between those two. So still pretty rapid growth, exponential growth for all three of these. Good. Okay, that's it for this video. We'll continue with graphing more exponential functions and then also looking at equations in the next 2 videos for this section.